So I think we can start now. Few people are joining still. Yeah, let's begin. So I think week 3 and week 4 lectures have been covered, and so I briefly went through the lectures, and I think dynamics and control are the major topics that have been covered in the last couple of weeks. So we will discuss a few questions from previous year assignments as we did in the last discussion hour, and that will help you to solve the assignments which are due next week. So yeah, let's begin. So the first question is based on the Lagrangian. So Lagrangian, as you know, is can be written as L is equal to K minus P, where K is the kinetic energy and P is the potential energy of the system basically. So in this case, we have a mass which is being dropped from a given height, and we have to find the value of Lagrangian at the moment when it hits the ground. So let's say there is a mass and it's being dropped from height h. Then at any instant of time, uh, the kinetic energy can be written as half mv square, and the potential energy is written as mg z, where z is the height from the reference surface, which is the ground basically. So the Lagrangian will be half mv square minus mgz. Now we have to compute this value when it's given that the mass hits the ground. So at that point z will be equal to 0. So here z is 0, and the kinetic energy will be equal to the potential energy at the topmost point, like at the point from which it was dropped. All that potential energy will be converted to kinetic energy when it is about to hit the ground. So basically or you can remember from like basic equations of motions also, that when a object is dropped from a height h, its velocity when it's about to hit the ground is under root 2 gh. So if we put these values in L, we will get basically we will get mgh. Z is 0 and v is under root 2 gh. And now you can put the values here. So m is 10, g is also 10, and height is 50. So the Lagrangian value would be, my bad, it's 0, so 5000 joules, right? Pretty straightforward, this question. Moving on to the next question. So this question covers the concept of Lyapunov functions. So we know that Lyapunov functions can be used to basically comment on the stability of equilibrium points of a dynamical system. So there are a couple of properties about which functions can be called as a Lyapunov functions. So you might recall that we can, the let's say a function is vx, then vx has to satisfy certain properties, that v0 is 0 and vx is positive definite, right? So This is a crucial property, and there are a couple of conditions. Yeah, also Vx has continuous partial derivatives, and regarding the derivative of v, so v dot 0 should be 0, and v dot x should be negative semi-definite, right? So we have to basically come up with a function which satisfies these properties, and if v dot x satisfies this condition, then we can say that the system is stable at that equilibrium point. And in case where v dot x is strictly less than 0, we said that the system is asymptotically stable. That is, when time, like on a long enough time horizon, even after small perturbations, the state would return back to the equilibrium state basically. When we say it's just stable, it will just not blow up, it will stay in the vicinity of the equilibrium point basically. So now there are a couple of Lyapunov functions given, and we have the system here. So yeah, so let's check both these functions. So the first function is here. Let's write both these functions. And when I denote this x with a bar, like this is a x vector, this denotes that a column vector containing x1 and x2 basically. So v1 is a function of both x1 and x2, right? So in the options, the first function which is given is 1 minus cosine x plus x square by 2, right? And the other function that's given is one minus cos, okay, here is x1 and here is x2 plus x1 square by 2, right? So we have to verify these conditions one by one on both these functions. So like the first set of conditions, that v0 is 0, is quite obvious. Cos at 0 is 1, and this will also be 0. So both these functions satisfy the criteria that v0 should be 0. And the next one is that vx should be greater than 0. So again, since cos x is less than equal to 1, so 1 minus cos x will be always positive, and square of a number is also always positive. So vx greater than 0 is also satisfied by both these functions. Now, so now we have to check the derivative of v to comment on stability, right? So if we find the derivatives of both these functions, v1 dot, right? So let's differentiate this. It will be sine x1.
Hello, sir.
Yeah. Any doubt?
Yes, sir. Your screen not just stand still, not moving. You are telling just like a differentiation integration. Just I am looking in the screen only one question number 1 in a week assignment number 3, week 3 question 1.
Okay,
Showing
is
in the
this
screen.
the same for every one of you?
No, sir. For me, it's visible. You just wrote v dash x equal to sine x1.
Yes.
And
So
it's visible.
who was facing this
Maybe
issue?
delay. Maybe sir some delay or some. Again rejoin. Should I rejoin?
Yeah, you can rejoin actually. I guess it's
Oh,
not an issue
okay.
for
Thank you,
others.
sir.
Might be a network issue. Yeah. So sine x1 and plus, it will be x2 2 and 2 will cancel out into x2 dot. So just keep in, okay, I missed a term here, wait. Yeah, so keep in mind that while differentiating, we have to first differentiate with that variable. Here is x1 and x2, and then differentiate them with respect to time also, because we are differentiating v with respect to time. So sine x1 into x1 dot plus x2. Yeah, are you able to see the screen now? It should be question 2. Yeah, so x2 and x2 dot, right? And to substitute, you can substitute the values of x1 dot and x2 dot as given in these equations. So x1 dot is x2 and x2 dot is minus sine x1, right? So basically it will be x2 sine x1 minus x2 sine x1, which is 0. Both them cancel out, right? And similarly, let's compute v2's differentiation with respect to time. So this will be sine x2 into x2 dot plus x1 into x1 dot, right? And x2 dot is minus sine x1, so minus sine x1 into sine x2, and x1 dot is x2, so plus x1 x2, right? Now in the first case, you can see that v1 dot x is identically 0, so this satisfies the stability criteria. It is stable. It is not asymptotically stable, but it is stable. It is always 0. In the second case, you can see that this expression, so sine x1 into sine x2, so sine x1, as you know, is always less than equal to 1, so this term will be less than equal to 1, right? So for you can find x1 and x2 such that this whole term would be positive, right? So this could be positive, so you can say that can be greater than 0, right? So this function does not indicate anything about stability, basically. So the correct option would be that v1x, which is this function, indicates that a system is stable at 0, 0. So the Lyapunov function is given, and you have to just verify these conditions, right? Let's move on to the next question. So there is a point mass, and basically it's a single arm manipulator with a point mass. It's not an extended mass, and we have a torque. So basically you have to find out the dynamic equation of motion. So you would have seen in the lectures how to find out equation of motion for various manipulators, like point mass manipulators or manipulators having distributed mass also. So this case is not much complicated. You can use your like fundamental concepts of angular momentum balance also to solve this simple problem. In complicated problems, we take the approach of finding out the Lagrangian and then finding equation of motion from there. So here you can just think that, let me like draw this once again. So let me draw it here only. So you know that here mg will act, right? Mg, and if you take components, it will be mg cos theta hit this side, and this will be mg sine theta, right? So if you write the angular momentum balance, so the first thing will be torque due to the weight, which is mg cos theta L, right? Now since this mass will be also, this arm is basically rotating and it will be accelerating also, so the acceleration will be theta double dot, the angular acceleration will be theta double dot, and we know that torque can be written as I into alpha, right? So since this is a point mass at a distance L from the axis of rotation, so its inertia is ml square, right? So the second term would be ml square and into angular acceleration, which is theta double dot, right? And this will be equal to the external torque, right? So this you can get from angular momentum balance, AMB, right? This is basically the, you can say, the R cross F term, and this is the I alpha term, right? And this is the torque. Now you have to just substitute the values. So m is given as 2 and length is 1, so 2 into 1 into cos theta into g is 10 plus m is again 2, L square is 1 square into theta double dot is equal to torque. So you can see that option C corresponds to this value, 2 theta double dot plus 20 cos theta equals tau, right? So this basically represents the equation of motion of this system. So given any theta double dot and theta, you can find out the required torque basically. Yeah, so this is a straightforward question with, you know that we use cubic polynomials to basically for defining trajectories of manipulators, and to parameterize those trajectories we give some initial conditions, sorry, boundary conditions, right? So for cubic trajectories, this is a third degree polynomial, how many conditions are needed? So for a cubic trajectory, yeah, so for a cubic trajectory we need 4 boundary conditions basically, right? This is mentioned in the lectures also. So you need, let's say this is 0 and this is 1, So you need x0, x dot 0, which is position and velocity at the first endpoint, and you need similarly position and velocity at the other endpoint, right? So given these four conditions, you can find out the parameters of the cubic polynomial, which has four unknowns, right? a0 plus a1x plus a2x square plus a3x cube, right? So four unknowns, and from four boundary conditions you would get four equations, and you can solve them to find out a0, a1, a2 and a3. So four unknowns, four equations, right? Similarly, if we take a fifth degree polynomial, we need six boundary conditions. So we add like acceleration conditions also at both the endpoints, right? Now the next question is that, let's say we have a system x dot is equal to f of tx, and u is an equilibrium point. So which of these conditions are true? So we know that at equilibrium point, x dot is 0, basically the derivative of the state is zeros, and that's what is the correct option basically. So not much to explain here basically, and it should be 0 for all time t greater than 0, for some t0 greater than 0. And once, let's say, you come at that equilibrium state, you will stay there, because x dot will become 0 and there will be no change in the state of the system until and unless it is perturbed basically. So you can just say from theory you can answer this. Yeah. So now we have a 2R manipulator, and point to note here is that it's a distributed mass system, it's not point mass system, right? So you have to carefully use this fact in your, and keep this fact in mind while doing calculations about kinetic energy, potential energy and all. So uniformly distributed mass. The parameters are given, length and mass, right? And we have to answer a few questions. So the first question is that the moment of inertia of link 1 about A and moment of inertia of link 2 about D is given by. So like you can either derive those formulae, but I guess in your like high school you have studied these formulae and it's just an application of them only. So if there is a bar, which is the case here, and if it's rotating about one of its endpoints, then, and this is of mass m and length l, then the inertia is given by ml square by 3, right? And same case if it's rotating about an axis passing through the center of mass, right? So in that case it is ml square by 12. So here you will see that for link 1 it's the first case. Link 1 is rotating about one of its ends, and since it's asked about point A, and for link 2 it's asked about point D, so this will be the second case where we have to find moment of inertia about an axis passing through the center of mass. So you can just straightforward use these formulae. ml square by 3, you can see that m is 8, l is 3, so you can find I about A for the first link is M1 L1 square by 3, which is 8, L1 is 3, so 9 by 3, so 24. And yeah, so it's given in terms of units, so units are fine. And I about D for link 2, you can use the second formula, which will give M2 L2 square by 12, right? So this will give 12 into 16 by 12, which is 16. Okay, so nothing much complicated here. Now following on the same system, we have to find the potential energy for link 2, and the state of the system is given in terms of the angles, basically the two angles. So this is a 2 degree of freedom system, as you would identify, and if we give theta 1 and theta 2, the system is completely specified. So at this given condition, basically we have to find the potential energy of link 2. So this is where I was mentioning that we have to keep in mind that it's a uniformly distributed mass system, it's not a point mass system. So like the go-to method would be, that okay, just find out the height of point D from the reference and just do a simple MGH kind of thing. But if you would do that, you would find that the answers are not there in the option. So we have to basically use integration to find out the potential energy of this distributed mass system. So let's do that. Let me first draw this once again. Okay, so this is theta 1, right, and theta 2 is given from the angle link 2 makes from link 1. So if we would count from the horizontal, this would be the angle that link 2 makes with the horizontal is theta 1 plus theta 2, and this is L1, this is L2, right? So let's say yeah, so let's say we take an element on the second link. So we take an element on the second link at a distance L, right? So that's what you do while finding out, let's say, moment of inertia or these kind of quantities for a distributed system. You take small elements and then integrate. So we take a small element of length dl at a distance L from this joint, right? And we would write the position of this dl element in the vertical direction, basically. So this is the vertical direction, y direction. This is the reference where PE is 0, right? So if you would write the position, it will be position of element dl in y. So you can imagine, first what's the height of joint to joint? The joint is at a height L1 sine theta 1, right? And from here we again go up L sine theta 1 plus theta 2, right? So first you compute this height, right? L1 sine theta 1, and then you compute height of this. So this is L sine of theta 1 plus theta 2. So the x position of that element is L1 sine theta 1 plus L, not L2, because we are taking an element at a distance L from that joint. L sine theta 1 plus theta 2, right? Now once we have the just a minute. So once we have the position of that element, now you can use the usual point mass formula to write its potential energy, right? So the potential energy of that small element, we denote it as dp, can be written as mass of that small element, dm, into gravity. So basically using the mgh formula, the basic formula, and this position, right? The position is L1 sine theta 1 plus L sine theta 1 plus theta 2. Cool. Now dm we have to find out. So let's say that rho is, let's denote a quantity rho, right? Let's denote a quantity rho, which is basically mass of that link m2 by length of that link. So this is basically mass per unit length, and then dm can be written as rho dl, right? Mass per unit length into that small length, that's the mass of that small element, and then the entire thing once again L1 sine theta 1 plus L sine theta 1 plus theta 2. Now to find the potential energy of the entire link, we have to integrate this from 0 to L2, right? That's the length of this link, right? So we have to do a definite integration of dp from 0 to L2. So let's compute this integral. 0 to L2, rho and g are constants, let's bring them forward, right? Rho g L1, I will write sine theta 1 as s theta 1 for brevity, and L sine theta theta 1 plus theta 2 and dl. So the integration is quite easy. It will be rho g L1 L sin theta 1 plus L square by 2 right, and now you have to put the limits from 0 to L2 basically. So at 0 both these terms will vanish, so we have to just put the values at L2. So this will be rho g L1 L2 sin theta 1 plus L2 square sin theta 1 plus theta 2, right? So one last simplification we can do is that, since rho is not a quantity which is provided in the initial question, so you can again use this equation that rho L2 is M2, so you can use this to eliminate or substitute rho. So rho L2 you can write as M2, so the first term will be M2G L1 sin theta 1 plus second term again 1 L2 will go with rho, so only one L2 will remain, so M2G L2 by 2 sine of theta 1 plus theta 2, right? So this you can say is the final form of the potential energy of link 2. So potential energy of link 2, right? Now we can just put in the values. So we have done the hard part, we have to just compute the numerical value now. So let's do that. I'll quickly see the values. M2 was 12, M2 was 12 and L1 3, L2 4. Okay, so the first term would be 12 into 10 into 3, theta 1 was pi by 6, so half, plus M2 is again 12 into 10 into L2 is 4 by 2, and since theta 2 is 0, so again this is again pi by 6 only, so 1 by 2, right? And this you can see is, so this is 180, first term is 180 plus the second term is 120, right? Yeah, 300 joules. I think, yeah, the option is that only 300. So this is how you can find the potential energy of a distributed mass system, right? Any doubts in this one? I think again this procedure of taking elements and integrating you should be familiar with, I guess. Now the third question on this system only is to find the kinetic energy of link 1. So this will not take much effort. So K1, you can straight away write this, there's no need of integration in this one. So because this is what you can see is that this link and this is point A, right? So this link is undergoing a pure rotation about this point, right? So what we can write is we can write the kinetic energy as half the moment of inertia about point A. This is the one thing to note about point A into the angular velocity square, right? So this will be half, and as I mentioned, the moment of inertia of a rod when it's rotating about one of its ends is ml square by 3, and omega is theta 1 dot, and the value is given as 2, so theta 1 dot square, right? Again we put the values. M1 is 8, I think. L1 is 3, and 4. So this will be 3 and this is 2, so 48 joules, right? Okay, next question we have. Let me just reduce the size of this one. Yeah, next question that we have is again a distributed mass system. So in the problem itself you can find a hint that you have to do that integration and all, and I think the similar system is there in your lectures also. It has been discussed, so this time I will just use the results directly, and either you would have done it while doing the lectures, or you can again follow the steps from the lectures to get the expressions. Okay, so we have to find the basically the torque when theta and theta double dot is given. So what you would need is you would need the equation of motion, because equation of motion relates the torque and the accelerations, right? And this this process of finding torque when theta and theta dot is given, this you also call as inverse dynamics basically. So I will just copy the result this time for the torque expression. So again, the kinetic energy, I will write the expressions for kinetic energy and potential energy. You should try to compute these expressions on your own, right? So kinetic energy is given by 1 by 6 m L1 square theta 1 dot square, right? And the potential energy is given as basically mg L1 by 2 into 2 minus cos theta, So again, for potential energy and for kinetic energy, you take an element, write the kinetic energy or the potential energy for that element, and integrate from for the entire length of this uh, rod basically. So you will get these expressions. Once you get these expressions, you will compute the Lagrangian. Lagrangian will be k minus p, right? When you compute the Lagrangian, then you will find out the equations of motion. So equations of motions will be given by tau is equal to d by dt del L by del theta 1 dot minus del L by del theta 1, right? This is how we find the equation of motion from the Lagrangian, right? So once you do all these computations, which once again I'm mentioning that it's there in the lectures, so you get the expression for the torque basically. So torque is 1 by 3 m L1 square theta double dot plus m g L1 by 2 sine theta, right? Now, so I hope no one would have any major issues on arriving at this expression. If otherwise, if like time permits, I can come back and revisit this one. But yeah, if you follow the steps, you will arrive here. And once you arrive here, this is the expression basically that you need to derive in order to find the torque basically. So now we have all the quantities that we need to evaluate this expression. We have the value of m, L1, theta double dot, and theta. So again, let's just compute the values. So torque would be 1 by 3 m is 10, L1 is 9, and theta double dot is 1. And m is 10, g is 10, L is 9 by 2, and theta is pi by 4, so 1 by root 2. So this is equal to 270 plus 225 root 2, and the units will be Newton meter. Okay, in case it's just given in terms of units, so let's not write the units. Okay, so yeah, this is how you can find, basically you have to find the equation of motion connecting the external torque or force with the accelerations, and then you can compute the values in the given data. So once again, a theoretical question based on Lyapunov functions. So yeah, as I mentioned while solving question 2, that Lyapunov functions should have continuous partial derivatives. So this is sort of just a fact, And yeah, any doubts in questions that I have discussed for this assignment?
Sir,
Yeah.
excuse me, sir. Question number 9. We are not given figure, so should we assume the figure which you have just shown for a single arm
This one.
robot? Yeah, yeah.
Where is the figure not given in the new assignment?
In assignment, yes, sir. In the assignment which we have,
Okay.
the diagram is not given. So shall we assume this? Because if theta which is shown about y, if it changes, then answers can change.
Does the question go like the wording of the question is similar, right?
Yeah, wordings are similar, values are different. So
Okay. So I guess yes, I think you can
yeah, because in
analyze with the same
grade,
same
yeah,
like
lectures also same thing was
yeah, same
told.
thing was there.
So we will okay, fine.
Yeah. Okay, cool. So let's discuss few questions based on week 4, right? So in week 4, control has been introduced, and I think some neural network approach towards controlling manipulators and doing inverse kinematics and all, I guess. So let's solve some questions based on these concepts. So we have the dynamic equation of a pendulum, and what's being asked is the control required to hold the pendulum at theta is equal to pi by 4. So for this question, even if you are not very much familiar with the all the theoretical background of control, you can find out the answers basically from your common sense, basically, that if you are holding the pendulum at a certain angle, then obviously its acceleration would be 0, right? So theta double dot would be 0, and theta is given pi by 4. So from the equation of motion, so we basically know the acceleration and the position that is required to evaluate this expression, and then we can find tau. So since we want to keep the pendulum at the same position, we are holding the pendulum, right? So theta double dot would be 0, and theta is given pi by 4. So tau is 0 plus k into 1 by root 2, which is k by root 2. Yeah, so not very long calculations needed here. Okay. Yeah, so again, expression for torque has been given for a 1 hour manipulator, and theta d is the desired trajectory, and e denotes the error between the desired trajectory and basically the actual joint trajectory, and we are applying a PD control. So the question says that the torque value that we would apply looks something like this basically, right? So basically what we are doing, we are replacing theta with e plus theta d, right? And e dot would be theta dot minus, let me just write it. So e dot would be theta dot minus theta desired dot, and so since why we are, so how we can where you can see that it's a PD control. So from this term basically, this KE is the proportional term, right? K into the error between the positions or joint angles, and this is the D term. So error between the joint velocities basically, and these K and L are called gains. So what we are trying to do is that we are trying to compensate for errors in joint positions and joint velocities. We want our actual trajectory to be as close as the desired trajectory, right? So the desired values generally we have these desired values, and we want to know the torque basically, which we would have to apply on this one arm manipulator in order to make it track this trajectory as close as possible basically. So in like, if you would like to, let's say, simulate this system, or let's say you have a manipulator and you want to make it follow a certain trajectory, then you would have to appropriately find out the values of K and L, right? So that so it's not as if any random value of K and L would work, right? So you would have to tune those values. So that's called tuning the controller basically. So you have to tune those values so that you get a good performance, and ideally you would want to see that the error goes to zero as t tends to infinity basically, like on a long enough horizon the error is negligible. So that's the requirement that we have. So again, this question is based on a similar example we have in lectures, right? And there, if you would recall, if you have the lecture handy, you can see the similar system with a similar equation. And what we arrive at finally is that we arrive at a certain equation like this. So W double dot plus LW dot plus W is equal to 0, where W is E dot basically, the difference in joint velocities. So is everyone familiar with this expression? Like this is there in the, this has been derived in the lecture, so I'm not deriving it again. So you can look it up there, right? Oh, I missed a K here. Wait. Okay, so when we try to so this is the second order differential equation, and you solve this by substituting an expression of form like r e to the power I theta basically, and the solution, right? So you can solve it using, you generally make this substitution to solve an equation like this, Euler equation basically. So it will be like, if you substitute W in this equation, it will be R square plus LR plus K is equal to 0, right? So this is a quadratic equation, and the value of R will be minus, so you know the formula of the roots of a quadratic equation, so it will be minus b plus minus under root b square minus 4ac, right, by 2a. So now what we want that et should go to 0 as t tends to infinity, right? So we want that when we want to ensure that the real part of the solution is negative, basically. So r has a negative real part we want to ensure. We can ensure that if this part becomes imaginary, so minus L by 2 will take care of that requirement, right? So the condition that we take is that L square minus 4k should be less than 0. Okay. So now if you check for all these cases, right, let's check the value of L square minus 4k for all these cases. So the first would be 3 square plus minus will cancel out. So 3 square plus 8, right, that is 17, which is greater than 0. This looks like 1.7. Second case, it will be 1 square minus 4, which is minus 3 and less than 0. Third case is 2 square this will be again minus 4 less than 0, and fourth case is 4 minus 12, this is 16 and greater than 0, right? So we see that in the first case and in the last case, so options B and C satisfy our criteria, right? And option A does not satisfy, and option C does not satisfy. So like when I was doing this question, I think both of A and D are not possible, but I would say, if can any one of you comment on this, that why option A has not been selected here? Like I could not find a proper reason. If anyone could have something to comment on this, then please do. In my opinion, I think both A and D are not possible, but it could be that I might be overlooking some other condition. Okay, so yeah, so I would say that just verify this type of questions closely and see that if there are any other conditions that you need to check other than this condition, this L square minus 4k one, right? So just make sure about that. Yeah, so next question is also similar. So again there is a equation of motion, right? And we apply a PD control here also. You can clearly see the P term here, right, and the D term here. Okay, so again we want that same behavior, that theta and theta dot should tend to 0 as t tends to infinity. Then what are basically we have to find conditions on values of k1 and k2. So again we would go by the same approach. We would use we would again start off from here only, right? So yeah, So again, this is also similar. This is like ke plus le dot. You can think that the desired is 0. So this is theta minus 0 and this is theta dot minus 0. We have to. So the error one you can define here is theta minus theta d, and you can think that theta d is 0, right? So I'm just trying to draw parallels between, like this setup and this setup. Like if you see that, okay, you might think that, okay, this is e here and this is theta here, so there's something different, but it's not. Like it's the same setup basically. And let's again write that differential equation, that w double dot plus, so here you can see that it was ke and le dot. So again we write the same expression in place of k and l. Here it is k2 and k1. Yeah, to 0, w is equal to e dot, and yeah, e dot is equal to theta dot. Since e is theta, so e dot is theta dot, right? You can also, like, in this case w is also, you can write as e dot, so theta dot, right? Yeah, nevertheless. So again, the similar kind of equation and similar type of solution would be there, right? This type of solution would be there. And again, if we write the equation in terms of r, if we substitute w as r e I theta, then it will be r square plus k2 r plus k1 is equal to 0. Okay, so again we write the solution for r. This will be minus b by 2a plus minus under root b square I think there was an issue here also. K2 square. Yeah, let's do it slightly differently. So here what we have, like if you compare these two equations, tau is equal to ml square theta double dot mg l sine theta. This is the expression, and after applying control, this is ml square k1 theta plus k2 theta dot plus mgl sin theta. So basically what your control law here is, usually it's a PD control law. So we are doing a PD on theta, right? And if you like compare these two equations, you can see that theta double dot we are writing as k1 theta plus k2 theta dot, right? So theta double dot is k1 theta plus k2 theta dot, right? All okay till now? Now here, yeah, so now we come to that familiar differential equation form, that theta double dot minus k2 theta dot minus k1 theta equal to 0, right? And what we need theta tends to 0 and theta dot tends to 0 as t tends to infinity, right? So again we take theta as, let's say, r e to the power I alpha, right? Then we substitute, so we get r square minus k2r minus k1 is equal to 0, right? So r is k2 by 2 plus minus under root b square plus 4k1 by 2. Cool. So once you get the expression for r, and why we find the expression for r, because when r is, the real part of r is negative, right, the solution will die down basically. So real part of r should be less than 0. This is a condition, right? So the real part of r is this one. This means that k2 by r, sorry, k2 by 2 yeah, k2 by 2 is less than 0, and this means k2 is less than 0. So this condition we arrive at, that k2 should be less than 0. And again we want that this discriminant to be less than 0. So the other condition is k2 square plus 4k1 should be less than 0, right? Now if you check the options, so k2 less than 0 straight away points us to option B, but option B also has a second condition which says k2 square is greater than 4k1, right? So what I have solved, I am getting this condition. So basically this condition and the second condition that is given here are not the same, but I think that even if k2 square is greater than 4k1, yeah, then also this can hold basically. So yeah, again I would say that you might need to check this one on your part also. I would just write a comment here, please. Check the, if you go to this document once again, then please check the second condition. So first condition is clear, we are clearly getting that, and you can like find the solution also, but since it is a second condition also and the discriminant is not exactly giving this condition, right? Similarly here also, like should write a comment, please check if option A should also be selected, right? So just do some checks on your part also. Okay, so yeah, so in the lectures you have also moved on to biped robots, so basically moving on to actual applications of what you have studied till now, and a common, like a very useful concept in case of bipeds or quadrupeds also, like in general for legged locomotion, is the excuse me, so is the concept of zero moment point or ZMP. So ZMP is basically, when let's say a foot is in contact with a surface, so ZMP is a point in that contact area about which if you take the moments of all the forces that are acting, then the net moment in the horizontal direction is zero basically. That's why the name zero moment point. So like you can basically say that an equivalent amount of vertical force is acting at that ZMP location basically. So like if I just draw a representation, so let's say there are 4 points of contact, right? So points of contact are important here. Okay, and you have the forces at each of these contacts, right? You have forces F1, F2, F3, F4, right? So ZMP will lie somewhere here, right? It will be a point where the net moment due to all these forces in the vertical direction will be 0, and you can like replace this by just a net force acting on the ZMP. These two are like equivalent kind of thing. So again, it is asked that which of these quantities are not required while calculating the ZMP. So you have that expression of ZMP, like a formula for ZMP in the lecture notes, and you can clearly see that you don't need the torques to compute the ZMP, right? So you can get from C formula of ZMP, right? So as I mentioned, ZMP is used to describe whether the robot is in a stable condition or not. So it's given that a biped is there, which has a square foot basically, right? And you can imagine that let's say, let me do some drawing. So let's say there is a biped here and it has square feet basically, right? So the coordinates of those the foot is basically given. So let's draw that foot on a Cartesian plane. Right, so the coordinates are given as 0, 0, 4, 0, 4, 4, and 0, 4, right? So you know that the robot will stable only when the ZMP lies inside the support polygon or the convex hull of the support points, right? So two concepts, like a new terminology here. So has the term support polygon being used in lecture? Because I'm not exactly going through them. Can anyone confirm? Or convex hull? Okay, it's fine. So yeah, so ZMP, if for stability, ZMP should lie inside the convex hull of these points or the support polygon basically. If it lies outside, anywhere outside this is unstable. So this is stable, inside this is stable, and outside this is unstable, right? So what is being asked, that which of these coordinates cannot be, right? So first is 2, 3. So 2, 3 would lie inside, right? 3, 3 would lie inside. 1, 1 will also lie inside, but 6, 1 would not lie inside, right? 6, 1 would be somewhere here, and this would be unstable. So this cannot be a ZMP if we want a stable motion, right? So that's how you can comment on the stability using ZMP. Okay, so quickly moving on. So this question again. So now we have arrived on the concepts of neural networks basically, and the question being asked is that which of the following is not a sigmoid function, right? So first of all, what's the sigmoid function, right? Sigmoid function is given as right. I think this is the sigmoid function. Yeah. So like we use sigmoid, so this is the actual sigmoid function, and but there are other functions also which have a similar kind of traits, right? So sigmoid function, how does it look like basically? Right. So basically it looks something like this, right? I could have drawn it better, right? Let me draw it here. Let this be y-axis. This is the x-axis, right? So when x is let's say x is infinity, right? So this term will go to 0, so the value would be 1, right? So this is 1, right? So asymptotically, as x tends to infinity, this goes to 1. Similarly, when x is minus infinity, so this will be e to the power infinity, and the denominator will be infinity, so this will be 0. So the value asymptotically goes to 0 as x tends to minus infinity. Now when x is 0, so this will be 1 by 2, right? So this will cross the y-axis at 0.5, right? So it will increase from here, right? And then right, something like this. Yeah, you can find better pictures in references, books and all, right? So just to give an idea of what we are discussing. So this is the actual sigmoid function, but we use like lot of a few different functions also have similar trend basically, right? So those are also called as sigmoid functions, and what we need to say here is that which of the following is not a sigmoid function, right? So the logistic function basically is also of a similar nature. So you can again basically search these functions, or if you know the function formula, you can plot them and see. And options C and D are, I think again, option C and D are the same because arctangent is also tan inverse, right? So this is tan H. Logistic function, I think I'm not recalling the exact form, but hyperbolic tan is tan hx. And arc tangent and inverse tangent, these two are the same, tan inverse x, right? So if you see the plot of tan inverse x, then you would see that it does not follow a similar trend, so you cannot classify it as a sigmoid function basically. This is a pretty straightforward question. Hyperbolic tangent function, as I mentioned, is tan hx, and in terms of exponential of x, it can be written as e to the power 2x minus 1 by e to the power 2x plus 1, right? So what you have to evaluate is at minus 1. So you need to just recall this, what's the form of the hyperbolic tangent function, and you can easily compute the value at minus 1. This, if you write e to the power minus 2 as 1 by e square, then you will get this. Which is the correct answer. Okay, so we have a neural network here, right, which has two hidden layers, and the input is x and the output is y, right? So basically we have the weights we have given, and we have to find the weights after the first iteration of gradient descent. So basically neural networks, what they do, they use gradient descent, they use to converge on a specific value of weights, the value of weights for which for given input it gives the correct output basically, right? So again, this question can be easily solved using the formulae given in the lecture notes. So like the weights, let's say u denote, I'm just writing a couple of general formulae, you will find them in the lecture notes also. So these are the weight vectors. Then what you do in gradient descent, so at k plus 1th iteration, the value is given as the value at kth iteration minus alpha times, alpha is the learning rate, the derivative of u at the kth time step, right? And similarly for v, it will be vk minus alpha times dvk, right? So the idea behind gradient descent is that if you go opposite to the gradient of a curve at a certain point, then you will get the maximum decrease basically. It's the direction of maximum decrease, the direction negative to the gradient of a function, right? So, and we want to converge on a value as fast as possible. So that's why we go in the direction opposite to the gradient. So since the initial conditions we have to consider as null, so all these four values would be 0, right? So the value of v1, v2, u1, u2 at the first time step can be given as the value at the initial value, that is at the 0th time step, minus alpha times, and we have the sigmoid function, so the derivatives and all, like again this expression I'm directly using from the lecture notes. You can see how it's being derived there. So this will be alpha times x into y comma y minus 0, right? And the derivative, basically derivative evaluated at this condition 0 0 0 0, right? So it will be minus 1 minus 1 0 0. What is this? This is derivative at 0 0 0 0. Okay, so if you put the values of x and y here, what you will get is zero, 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 and alpha is the learning rate. So basically, what learning rate is one, or what is called a hyperparameter, right? So learning rate will decide how fast the algorithm takes steps, basically. So basically you have to find out a sweet spot. Like the learning rate can't be, if the learning rate is very small, the progress will be very slow, right? It will converge on the values very slowly. So again, that would make the algorithm very slow, and it will take a long time. And if alpha is very large, then what you risk that you would not converge on the, you would not converge at the correct point. Basically you would go ahead of that. Let me give an example. So yeah, so let's say this is a curve, right? And you are using gradient descent to reach here. Basically you want to reach here, right? This is the optimum value. So if you are taking steps very slowly, that part is clear, like you would arrive here but very slowly. If you take very long steps, then let's say you come here at the first iteration, then if alpha is large, you can overshoot and you can come here directly, right? And then again it would try to go back in this direction, but since alpha has a large value, it would again come this side. So it will keep on oscillating like here. It would not converge on this value. So alpha has to choose very carefully. Choose alpha carefully. But you will find that typical values are there, so you can start off from those values and then tune it basically according to your problem. So here alpha value is given, it's 0.1, x is given to the input, y is 10, right? So if you if you simplify this, you would get right. So this is the value of the weights of the network after the first iteration. Right, after the first iteration. Okay. This question, I think this is based on. Okay, so first look at options. So this is the usual like manipulator dynamics equation, right? Where I guess you know the usual meanings of these symbols. So MQ is the joint space inertia matrix, V is the the Coriolis force the centrifugal force matrix, G is the gravity forces due to gravity, and yeah, I guess these two terms. Okay, let me just quickly pull up the lecture notes. So basically what is being asked is that which of these are correct. So MQ is always symmetric, so this is not correct. MQ is not positive definite, also this is not correct. So mass matrix is always like positive definite and symmetric, right? What is being asked is that so the two options remain is that whether, just give me a minute. Right, so yeah, so M is the inertia matrix, it's a square matrix, and it's always positive definite, right? And I think guys, so like is this equation, has this been discussed as it is in the lectures, or is this new for you? Because let me know where, in which slides I can find this. Yeah, here it is. Right. So for an N-link manipulator, MQ is the inertia matrix. This is the centripetal and Coriolis matrix. G is the gravity defects. Yeah. So FR is representing the friction effects. TD is a vector of unknown but bounded external disturbances, right? Unmodeled dynamics. And tau is the torque input. Okay. So the first property is inertia matrix is symmetric, positive, definite. So that gives us, oh wait, right, so that we have checked out that MQ is symmetric and positive, definite. Next is that the inertia and Coriolis matrix satisfy the following skew symmetric relationship. So this is the correct option, right? Okay, so the proof of this relation, like I'm not exactly sure of as of now. I would have to check the proof of this property. I think it's not there in the lectures also. So this I would have to check, and I might discuss in the next week's discussion. I'll take a note of this. Right. By the way, this is true for like any skew symmetric matrix that let's say if A is skew symmetric, then if like A belongs to R n cross n and we have a vector x belonging to Rn, then you can verify that x transpose A x is always 0, right? So like you can use it as a, like every skew symmetric matrix satisfies this property, right? You can verify this one easily. For this property I would have to check once again like how this comes up. So I think we have one more question, yeah, and just enough time for this. So again, it's a formula based question to compute the pseudo inverse of a matrix. So let's say, so why do we use pseudo inverses? Because not all matrices are invertible. Inverse can only be found for square matrices, and that also non-singular matrices. So for all other cases we define pseudo inverse, right? So this is also so pseudo inverses are of many kind, but the most common one is the Moore-Penrose inverse, right? Moore-Penrose inverse. So what we do that a pseudo inverse, again we can define pseudo inverse in two ways. Moore-Penrose pseudo inverse in two ways. First is what we call as the left pseudo inverse, and why we call it left pseudo inverse would become clear in just a moment. So A transpose A inverse A transpose, right? This is the left pseudo inverse. And why left? Because if we would see A pseudo inverse A is identity here, right? So point to note here is that in normal inverse what we say is that A inverse A is equal to A inverse is equal to identity, right? But here if you define A inverse as this, and if you try A pseudo inverse, right, then it will not come as identity, it will come as anti only when you pre-multiply with the pseudo inverse or multiply on the left side. So that's why it's a left pseudo inverse. And similarly, as you would expect, there is a right pseudo inverse also, right? And it is defined as just like in the opposite order of that, A transpose A transpose inverse. This is the right pseudo inverse, and in this case only this will be identity, A pseudo transpose inverse. Cool. And in this case this one will not be identity, so we have to be careful with that. And one more point to note is that A need not be square. A can be any A can be any rectangular matrix. So A belongs to R m cross n, right? And note that A transpose A or A transpose is square, right? So A transpose A will belong to, right? A transpose A belong to n cross n, and similarly A transpose will belong to m cross m. So for these two matrices we can do the usual inverse, right? So that's why we are using the usual inverse symbol here. Yeah, so here I guess usually left pseudo inverse is commonly used, so you can use the formula to compute the pseudo inverse. So this is how we can justify it, is that it's a left one, because this is a 2 cross 3 and this is a 3 cross 2. So you have to multiply this, pre-multiply this basically to get the identity one, right? So this is a left pseudo inverse, left pseudo inverse, and you can use this formula to compute that. Okay, so yeah, that was it from my side. I think we are just in time. Okay, anything else quickly if you want to discuss, or any comments on today's discussion? Okay guys, so yeah, so that was it for this week. I hope you are able to solve your assignments, and we will meet next week at the same time. So thank you guys, see you,
Thank you, sir.
bye.
Thank you, sir.